Welcome to our Ada Core webinar about CodePeer 2.3. This is the most recent released version of CodePeer, and this seminar will be introducing you to the new features of CodePeer 2.3 as well as the features that CodePeer 2.3 shares with all of its predecessors. So just a quick summary of what's new in CodePeer 2.3, and we'll come back to this later with more detail, but just to give you a sense of what's new, if you've already been using CodePeer, this is some of the newer features. Ada 2012 is the latest version of Ada, and if you followed that development, you will know that Ada 2012 includes a number of features that are oriented around high integrity software, and particularly the notion of contract-based programming, where you can specify pre and post conditions for every subprogram, as well as things like type invariants and so on. And that goes very well with CodePeer. It has a orientation towards contract-based programming, and in fact it helps identify contracts in existing code that might not have them explicitly indicated. And so the two really go hand in hand. Another area of enhancement in CodePeer 2.3 has to do with floating point computations. In the past, those were done using essentially infinite precision arithmetic, and now we have more precise simulation of what typical IEEE float hardware does. Other important features are the identification of uninitialized global variables. In the past, we focused more on variables that were initialized or uninitialized within data structures and so on, but not necessarily those that are initialized during library interlaboration, and that is now part of CodePeer's standard capabilities. We've also improved the user interface available within the GPS, the GNAT Programming Studio IDE associated with race conditions, and more generally all of the CodePeer features. There's an updated user interface. We have begun to incorporate the notion of the common weakness enumeration, CWE, into some of our tools, and you'll see this increasing as in future releases of CodePeer as well. Right now it's available as part of our capability of exporting a Excel compatible spreadsheet. We can include the CWE message IDs within that. We're always working towards reducing the number of false positives, or so-called false alarms, within the output, and we've made more progress there. This is what we would call the never-ending full employment theorem. We could never actually get rid of all of them without introducing false negatives, thanks to the so-called halting problem. It's impossible to fully distinguish between correct and incorrect programs in some deterministic way, but we are getting closer and closer. And finally, a very important feature is that now when you receive CodePeer, it's a standalone product. It's fully encapsulated. It includes the parts of the GNAT compiler front end that are needed to do static analysis. What this means is that you don't have to worry about installing identical or compatible versions of the compiler, the GNAT compiler, and the CodePeer tool. They will work side by side even with different versions. And if you want to upgrade one and not upgrade the other, or upgrade them to different levels, that's totally possible. It also means installation is somewhat simpler. Anyway, these are all nits if you haven't got the whole basic idea of CodePeer, and that's what we're going to focus on initially. So what's the main point of CodePeer? It's to improve the robustness of your code. And in particular, does it actually handle all possible inputs properly? It's hard to write sufficient tests to really ensure that, and it turns out that the kind of advanced static analysis that CodePeer does is able to answer that kind of a question much more authoritatively than just saying, well, we ran a lot of tests and we hope we covered all the relevant input. CodePeer uses a mathematical approach which allows you to have much more confidence in the answer to that question. Further along, there are certainly many runtime checks and compile time checks in Ada, but there are some things which are not generally checked at runtime in Ada, basically because they represent too much overhead. When you're doing static analysis, you can afford to make those sorts of checks and do them all effectively at compile time. It does a very sophisticated mathematical approach which allows it to do these kinds of checks, in particular finding uninitialized variables. Typically, if you have an uninitialized variable, a runtime test might just bump into junk, or it might be irreproducible problems and so on. That's something that static analysis tools are particularly appropriate for. If one of your goals is to test every line of code, if you've got unreachable code, that makes it a little harder to test every line of code. So one of the things that CodePeer does is it tries to identify pieces of a function or procedure that cannot be reached because of probably a logic error in the original code, but it will identify those places. Race conditions, another thing where it's difficult to create runtime checks, and it's difficult to write tests in particular that will identify race conditions, but this is something that our static analysis tool can do. Race conditions, what we mean are data-oriented race conditions. That is, you've got a single shared data object, and you've got two logical threads of control, two Ada tasks that are potentially accessing that single data object simultaneously or concurrently without adequate synchronization. And again, that's something that's very hard to test for, and most compilers can't really detect it, and the runtime checks are not really helpful there. So that's something where a static analysis tool is really the right answer. And finally, the whole idea of exceptions. That's the basis of Ada's runtime checking, but in a lot of release software, you really don't want to have exceptions that are being raised. So any place where an exception might be raised, we try to help you identify that and identify the conditions under which it might be raised. Another very important feature of CodePeer, which is perhaps not shared with all static analysis tools, is it's very much focused on helping the reader understand the program that they are reading. What it does is it actually generates as-built documentation for every subprogram, every function and procedure in the program that it analyzes. And this is human readable as-built documentation in the form of pre and post conditions, which are extracted from the algorithm of the program itself, identification of what are the inputs, what are the outputs, including global variables. Also, it generates other kinds of useful information, such as so-called test vectors, which we'll see in the demonstration, and so on. All of this is very useful when you're trying to do let's say, a code review of the source code that you may not have ever seen before, or maybe you wrote it, but it was a while ago. This can remind you or inform you of important properties of the code as built. There may be documentation that exists, but it may not necessarily perfectly match what the code itself is doing, and the CodePeer generated documentation is pretty well guaranteed to represent the true state of affairs. So we'll see a use of CodePeer fairly shortly, but it's really quite simple to install in these days. It's gotten simpler as it's moved along in its version numbers. As I mentioned, the biggest change now is that the GNAT front end is now bundled within CodePeer and is not separately installed, and can be installed next to a different version of GNAT without any problem. You also don't need to use the GNAT compiler at all when you're using CodePeer. It is designed to be usable with any Ada source code that might be being compiled by other Ada compilers, and we're continuing to make that process easier and easier so that CodePeer can adapt to your particular compiler's quirks to some degree, particularly in terms of the sizes of predefined types and so on. It uses the same basic project mechanism and project build mechanism that is used with the GNAT compiler, and that means that if you're familiar with that, it's that much easier. If you're not familiar with that, it's a set of tools that are widely used and have a long history and have been getting friendlier and friendlier over the years, and so CodePeer is piggybacking on that mechanism. It's not like some relatively infrequently used tool which has its own quirky IDE. It piggybacks on the quite well-defined GNAT compiler IDE called GPS. Because of the integration between CodePeer and the GNAT and other Ada core tools, using CodePeer is extremely easy. Basically, it's a one-button mechanism, which we'll see in the demo. You define your project, and then you click on the Analyze All, and CodePeer does the rest of the work for you. Once it's done its analysis, it puts up a top-level code view report, And from there you can drill your way down, all the way down to the particular line of code where CodePeer thinks there might be a problem. At each stage it provides some summary data in terms of how many problems of various categories it found, what ranking we have assigned to it, which you can also overrule with your own ranking mechanism. We have high, medium, low. We also have some messages that we don't show at all, but you can turn them on, you can see them, and so on. Many of these things will be more obvious in the demo. So this is what I would call a spaghetti and meatball diagram, spaghetti and meatballs, and there's no quiz on this next period, but it is helpful, I believe, to have a little bit of an intuition of what's going on behind the scenes with some of these tools. If if they're just magic, then you don't really know what's going on. You're not sure you might trust them, and maybe you don't necessarily know how to use them in any intuitive fashion. So this is giving you, hopefully, a little bit of an image of what's going on behind the scenes with CodePeer. As I've mentioned, it does bundle in a part of the GNAT compiler and the so-called front end of the compiler that reads the Ada source code and generates an intermediate representation for that, which we call the GNAT tree. And that's coming in the upper left corner of this diagram. And that input, or it's the output of the front end, it's the input to CodePeer's engine, if you will, is translated into a relatively language-independent, target-independent representation, which we call SKIL, which stands for Statically Checkable Intermediate Language, particularly well designed for doing further static analysis. And we translate all of the GNAT trees for each of the source files you would like to be analyzed into this SKIL representation. And that's all done at once, or once you've done it once, you don't have to keep doing it. So if you make a small change, you don't have to regenerate all the SKIL. It'll just generate the stuff that corresponds to newly altered source code. And then CodePeer is initiated once you have finished generating all of the SKIL for your Ada source program. So CodePeer in that sense is more like a builder. It runs after you've finished compiling the source code of interest. One of the features of CodePeer is you don't have to compile everything. You don't have to convert everything to SKIL. You can have pieces of your system that are incomplete, and CodePeer will do its best to fill in the gaps, making appropriate assumptions about code that's missing. It can be set to work on a single package or on a library of packages or on a subsystem of packages, or in various combinations. It basically, any subset of your source code that can be compiled can be analyzed. So what does CodePeer do? It starts by visiting every subprogram in the code for which it has SKIL, and it tries to figure out, well, what are the properties of this subprogram? And it records that in in these so-called annotations, which essentially are a summary of what the features of the program are, of the subprogram are. And it does this for all the subprograms. It iterates if the subprograms are recursive, and it deals with looping and so on. And it spends a certain amount of time doing this analysis. And once it's all done, it's then able to now go back and walk the SKIL for one final time and generate messages wherever it thinks that a problem might occur. And we'll talk a little bit more about what that involves. And when it finds an issue, it generates XML. It also generates XML for all of the pre and post conditions it has inferred from the source code. And that ends up going into a database which records the output of every execution of CodePeer, which allows you to do nice, interesting comparisons between different runs, different versions of your source code. And then that data can be viewed in various ways. GPS is the way we're going to demonstrate. It also has a web interface, and that web interface it can be viewed using any browser. We also have a special server which allows you to interact with the web-based output and update the database if you want to create comments on CodePeer's output, which we'll again talk about during the demo. Okay, here's a quick screenshot. I suppose it's a little bit of an eye chart because some of these numbers are fairly small, but just to give you a feeling for what we're going to be seeing in the demo, the main CodePeer report window is that part on the top third there with the various color bars. Those bars correspond to high ranking, medium ranking, and low ranking messages. In this case, there are no high ranking messages. There are a total of 12 medium and 5 low. Over on the right, we see the various categories of messages, and you can check or uncheck the ones that are of interest to you now. So if you're trying to focus on a particular thing, such as unused assignments or index out of bounds or null pointer dereferences and so on, you can choose just to focus on those, or you can turn everything on. You can also choose to focus on higher ranking messages before you are burdened, let's say, with a number of lower ranking messages, and so on. And that's all controlled by these checkboxes on the right. In the middle here, we have the actual source code of a particular piece of the source of this application, and we have an example of as-built documentation. The gray part there, if you look carefully, you'll see line numbers that are to the left of the source code, 41, 42, 43, and so on. There are no line numbers next to those comments that are in gray because those comments were actually generated by CodePeer. They're essentially the as-built documentation that I described earlier. And anytime you run CodePeer, those are provided to you, so you can bring up a CodePeer representation for doing your code reviews, which can add a lot of helpful information and so on. And again, I'll show you that. And at the bottom, if there are specific messages that CodePeer has produced, then those will be down at the bottom there, and you can see that we have highlighted one of them. And if you can read it, you got to get on your reading glasses here. It says medium warning, suspicious precondition for last, not a contiguous range of values. And I'll actually go through an example that has that particular message, and I'll explain it. But anyway, that's the basic structure of the layout. And over on the left, we have the actual source files of your project. So what's going on behind the scenes? I gave you that spaghetti and meatball diagram, and now I'm going to talk about what's happening inside that CodePeer circle that we saw on the diagram. In particular, what it's doing is it's trying to simulate what will happen at runtime. And for every variable and every expression in your program, it's trying to figure out that at that point in the program where this variable is referenced or where this computation is performed, what are the possible values for any given input. So of all the possible inputs, what could that turn into be as far as a set of values for this particular variable? So we have an x somewhere in the program, and at different points, CodePeer is able to determine, well, in this particular place, we know that x is going to be in the range 3 to 20. And over here, because of other things that have happened or other things that the program has done, we now know it might be in the range 1 to 10. So it knows, it's able to infer from the source code the ranges of every variable, and if it's a pointer, it can determine where it might be pointing, and for objects, larger objects, it can determine what might be the values in each of the components, whether the components have been initialized or not, and so on. So it does all of this analysis, and the purpose of doing all that analysis is so that when you use one of those variables, such as x, in a context where it's not allowed to be certain values. For example, you use x as an index into an array that is from 1 to 10, and CodePeer can determine, well, at that point, x might actually have the value between 3 and 20. So there's a little bit of a problem here because x might be larger than 10. So there is the possibility that array indexing might fail at runtime. And if you've suppressed runtime checks, well, that means it might do something really odd. And these are the kind of problems you want to identify earlier, obviously, rather than later. Some of them will be picked up with tests, but it may be that only certain inputs cause X to be out of bounds, and it may be that some of your tests don't have those inputs. So you may not actually detect this problem until later, and the worst case, of course, is you don't detect it until it's in the customer's hands. So the whole point of CodePeer is to effectively test your program using a mathematical approach before it gets very far along. And when the code is fresh in your mind, you just wrote it, and now the next night or even that same day, CodePeer is telling you, well, there's kind of an issue here. So it does this for every subprogram and every variable and subexpression and so on. But there's also the issue that the data in a given subprogram is coming from the outside world. And so we have to deal with that kind of data. And this is where the notion of pre and post conditions becomes very important. And in particular, when CodePeer, let's say it has a procedure that has two inputs, x and y, and inside it adds x plus y. Well, it immediately has to worry about overflow because maybe x is already a million or a billion, and y is also, you know, 1.5 billion, you add them up, you get a big number, and that number might no longer be representable within the size of integer that you're using. Typically 2 billion minus 2 billion and plus 2 billion is your 32-bit integer, so it is always possible that you could have a numeric overflow. It's not as likely as other problems. Another problem might be that you use x plus y as an index into an array. Maybe x is the starting point and y is the offset. And now we're talking about something that might only go from 1 to 100. And now if CodePeer can say, well, there's a real danger that x plus y might be outside the bounds. What it does is it propagates these issues up to the beginning of the subprogram. And if x and y are inputs, it's going to basically push this requirement that x plus y be in the range 1 to 100 onto all the callers. And then at each point of call, we're going to recheck this inferred precondition. And therefore, we propagate back to a point where perhaps x and y are coming from the disk or from the user, from a database, and so on. And that may be the place where the actual check should be performed, because that's really where you want to validate that the inputs are reasonable. If you wait until you use them deep within the subprogram, it's a little late to figure out, well, where did this bad data come from? CodePeer can back this up to the point where the data originally came from the user or database and so on. And that's where you really would like to know, oh, well, you know, here's where you should have checked to see if x was in an appropriate range. Post conditions are sort of the opposite side of the coin, where having assumed that the data now meets the inferred preconditions, we try to determine, well, what are the possible values of the outputs? Presume, let's say, z is a global variable updated by this same procedure. CodePeer can determine, well, presuming x plus y is less than in the range 1 to 100, then by the end of this procedure, z is going to be in the range 2 to 300 or something. It determines it based on the algorithm. It's inferring all of this from the algorithm itself, as built, as I said before. Other kinds of outside world issues is you may have, as I mentioned, CodePeer can deal with partial programs. You don't have to give it the full program to analyze. And you can actually have situations where you analyze a procedure that calls something that CodePeer is not analyzing. Runtime routines are a typical example of that. It might be a third-party library which you don't have access to, or you don't have any great interest in doing a full analysis of. So CodePeer tries to determine, well, what assumptions are you making about the values coming back from code that was not analyzed? So if we call some routine, it might be an IO routine, you know, get data from user, and then you immediately assume that those numbers are in some range. Well, we document that you're making that kind of assumption. We call them presumptions. You're presuming that this routine returned a value that had these properties. If you call a function and it returns a pointer and you immediately dereference that pointer, you're obviously presuming that the pointer is non-null. Other kinds of assumptions like that are all documented for you in the area we call presumptions, and I'll show you an example of that in the demo. And finally, their other source of outside data are global constants, global tables. And CodePeer is smart enough to figure out, well, what are the values stored in those global tables, so that if you use them in your algorithm, it knows what the range of those values is as well. Okay, and I don't want to go through all this, but one of the things that is worth emphasizing is CodePeer works on its own, can work overnight. It's one of the pickiest reviewers you will find around. It looks at every line of code. It considers every possible value for every input, and it provides as-built documentation that tells you not only numerically what are the possible values, but it might also tell you symbolically. For example, it might tell you that x must be less than y for this routine to work. It doesn't necessarily say that x must be in this range or y must be in that range, but it knows that x must be less than y. And similarly, when you're all done, you might know that z is going to equal x plus y times 3. Again, it doesn't necessarily know what the values of x and y are, but it can tell you a lot about the properties of the outputs as a function of the inputs. So it does things both symbolically and numerically, and it does it while you're asleep, which can be very nice. It does it before breakfast, after dinner. It's happy to work tirelessly on your behalf. So I think at this point we might jump to the actual source code. Let me just quickly review the kinds of checks just to give you a sense of the thing that CodePeer is able to identify. Array index check, we talked about that as an example. X plus y used as an index. CodePeer worries about the possibility of a index being outside of the bounds. Dividing by 0, always something you want to be avoiding. Tag checks is a feature of Ada's object-oriented programming, having to do with what sort of conversions you can do, and CodePeer worries about that. Discriminant checks has to do with variant records and whether you're using the appropriate variant. Access checks are another word for null pointer dereferences. Range checks, we talked about that, the range of numeric values. Overflow check is where it's not a specified range like 1 to 100, but rather just a physical range, like minus 2 billion to plus 2 billion, where if you go outside that range, the hardware will wrap around. And finally, this notion of preconditions, and we'll illustrate how that's not sort of a built-in check of the language, but it's a feature of CodePeer that it can propagate a precondition from one level to another, all the way to the point where the root cause, if you will. Users can also write their own assertions in Ada with a pragma, and in Ada 2012 you can write your own preconditions and postconditions, where effectively assertions that are associated with calls. CodePeer will analyze all of those and try to identify those ones that might fail and those ones that it knows will succeed. Also, anytime the programmer just writes, well, if blah, then raise some exception, that's effectively the user writing a specific check at runtime, and CodePeer treats those pretty much like regular runtime checks. It's trying to identify, could you end up raising an exception there, and if so. I mentioned uninitialized variables. That's a very important feature of CodePeer and is critical in certain kinds of static analyses. And finally, there's code that it's not necessarily wrong, but it's a little suspicious. So these are treated as warnings having to do with redundant code or dead code. You do a computation and then you immediately overwrite the result. So that would be an unused assignment where you assign a value, then you don't look at it or you overwrite it. And there are various other things which we consider suspicious. For example, if x is greater than y, then blah. And by the time you get to that point, CodePeer knows x is always greater than y, so that condition is always going to go the same way. And certain of the standards like DO178C at level A and so on, that's not a good thing to have a condition that's always going the same way, because they'd like you to test every condition both ways. And if it's always going the same way, that's pretty hard to do. And finally, there are other things relating to inputs and so on, and I'll illustrate some of those in our demo. Race conditions, I mentioned those. There are various kinds of race conditions. We're not going to actually illustrate this, but it is an important problem for certain kinds of programs, and it has to do with when you have multiple tasks, potentially referencing the same piece of shared data without appropriate synchronization. CodePeer is able to identify those places. Okay, so this is a good point for us to switch over to our demo.